Okay guys, in this video we are going to be talking about phase diagrams of binary liquids. And so just to clarify, a binary liquid or binary mixture, we're talking about two volatile liquids in these types of solutions. So both liquids have relatively high vapor pressures and low boiling points. And we'll be considering equilibrium between the liquid components and the vapor components. And so this is really something that we've already covered in a previous diagram, and so this is something that you'll definitely see on your assessment. Pressure composition diagrams at the level of ideal solutions, where you're looking at Raoult's law. So if you wanted to take an ideal solution and plot the total pressure, the total vapor pressure of the solution as a function of the mole fraction of the liquid. So this would be the mole fraction of component A in the liquid. You can use Raoult's law to evaluate what that expression would be, and it's linear. And so you would get a graph that looks like this. So this would be the total vapor pressure of the solution as a function of mole fraction of component A. When the mole fraction of component A is 0, that means you have pure component B. And so this is the vapor pressure of pure component B. When the mole fraction of component A is 1, that means you have pure component A. And so this value is the vapor pressure of pure component A. And it's just, for an ideal solution, it's just linear between the two. This is a problem that I believe we've already solved this problem for benzene and toluene. I think our pressures, it was at a different temperature, so the vapor pressures were slightly different, I believe, in that problem that we solved. They want you to calculate the vapor pressure, partial pressures, and total pressure for an equal molar solution. So they want the mole fraction of benzene to be 0.5 and the mole fraction of toluene to be 0.5. And so you really just need to execute the type of problem that we did in a previous video. And so I'm going to go ahead and skip the details here since we've already done it. We'll move on to the next kind of idea here. And this one's a little strange, and I'm not sure how useful it is, but in any case, you'll see this discussion in the textbook. So here what we're doing, these are some calculations that you want to be able to do. Calculate the mole fraction of component A in the vapor phase. Okay, so the symbol X is being used to denote the mole fraction of component A in the liquid phase. X is used to denote the mole fraction of component A in the vapor phase. And just to clarify, let me draw a diagram. I usually put this on the board in class. So we've got a binary liquid. We imagine we've got a sealed vessel. Here's our liquid phase. Here's our vapor phase. And now we've got two components in this solution. And they separately, they come into equilibrium with their vapor. And so there's going to be a vapor pressure for component A in solution, a vapor pressure for component B in solution, and these add up to the total vapor pressure of the solution. And then you also have, for pure component A, it would be PA star for the vapor pressure of the pure component, and then you would also have, you could do the same thing for pure component B, PB star. And so this diagram kind of highlights some of the notation. Let's say here we would have XA plus XB equals 1. So the mole fraction of component A in the liquid phase plus the mole fraction of component B in the liquid phase equals 1. Similarly, you would have in the vapor phase this, where YA and YB are the mole fractions of component A and B in the vapor phase. And these two mole fractions are not the same. What you find, as we've discussed previously and is written here on the slide, the vapor is enriched in the more volatile component. So whichever of the two components has the higher vapor pressure, that component, pure vapor pressure, that component is going to have a larger, the mole fraction will be enriched relative to the liquid phase. So if component A is more volatile than component B, then YA is going to be larger than XA. That's what that means. The vapor phase is more enriched. I should say that's what I mean by it. So in any case, what's going on in this equation here is we're developing an expression for the total vapor pressure in terms of the mole fraction of component A in the vapor phase. And then this equation here, this is the mole fraction of component A in the vapor phase compared to the mole fraction of component A in the liquid phase. And so those quantities are being plotted here. And so you're plotting mole fraction of component A in the vapor phase as a function of the mole fraction of component A in the liquid phase for different cases. Okay, so these different curves, they correspond to different ratios of PA star over PB star. So when PA star over PB star equals 1, that means that the two components are more or less equally volatile. When that ratio is 1,000, that means that component A is much, much, much more volatile than component B. And so what they're basically showing you is that when component A is very volatile and you have, I don't know, let's just choose an equal molar mixture. So let's just suppose that we've got a liquid phase that's 0.5 molar and we're comparing different types of solutions. When the two components of the solution have the same volatility, you find that the vapor phase is also 50-50, with respect to the mole percent. But if component A is much, much more volatile than component B, then for a liquid mixture that's 50-50 mole percent, you'll find that the enrichment, that is what the mole fraction of A is in the vapor phase, is very large compared to the liquid phase. That's all this graph is showing you. This one is even stranger. I don't know exactly why you would want to plot this. But anyway, they're plotting the total vapor pressure divided by the vapor pressure of component A star as a function of the mole fraction of component Y. So they're basically plotting this function here. I find it very difficult to understand it. So I'm really just going to skip it. I'll let you read the textbook's narrative on it, and if you find something useful in it, then great. If not, I'd recommend moving on very quickly to the next topic. So what we're going to talk about next is a temperature composition diagram. And what this shows, this is more like a phase diagram. It shows the composition of the phases when they are in equilibrium as a function of temperature. And it's a little bit strange to work with these diagrams because you kind of need to think differently about the diagram. In my opinion, you have to think sideways, and so that's why I put that note in here. So here's the setup. It's basically the same picture that I drew you before, except for there's a piston that is used to keep the pressure fixed at 1 atmosphere. And then what we're going to be doing is we'll be looking at the liquid and the vapor phases when they're in equilibrium at the mixture's boiling point. Okay, so we're going to be basically boiling the solution and evaluating what are the concentrations, the mole fractions in the liquid and the vapor phase. And again, the rule is that the vapor is always enriched in the more volatile component, which has the lower boiling point. So here's an example of a temperature composition diagram. So you're plotting temperature as a function of mole fraction. Okay? And there's actually two curves being plotted here. The bottom curve corresponds to the mole fraction of component A in the liquid phase. The upper curve corresponds to the composition, the mole fraction of component A in the vapor phase. Okay, and so that's why it's called a temperature composition diagram. Okay, and there are three phase regions. Down below the blue curve, we have the liquid. The liquid is the stable phase. Up here above the red curve, the vapor is the stable phase. And in between the two curves, we've got vapor and liquid in equilibrium. Now, here's how to think about the diagram. So suppose that we've prepared a mixture, a binary mixture, with a particular mole fraction. And so that's this vertical axis that represents the mole fraction that we prepared. And we start heating it up from room temperature. And then once we get the temperature high enough, that liquid phase is going to start to boil. And so a question you can then ask is, when the solution is boiling, okay, so when your liquid phase is in equilibrium with your vapor phase, what is the composition, what are the concentrations in the vapor phase? You obtain that by making a horizontal line. So you go up, and then at this point, there's a horizontal line here where the solution is starting to boil, and then you draw a line over to the vapor composition curve, and then drop all the way down here. That mole fraction, okay, whatever that value is along this axis, that would be the concentration of component A in the vapor phase. You could imagine continuing that process. So what if you collected that vapor, okay, and condensed it down? You know, you took the vapor at this concentration and cooled it down until it was a liquid, so you'd be down here somewhere, and then you took that liquid and heated it back up to a boil. Well, because the vapor phase is going to be enriched in the more volatile component, you would then have which is component A in this case. So notice, I forgot, I should have said that first. So take a look at the two extremes here. Should have looked at the ends first. Right, so this is component A along the x-axis. Here we have pure component A. This point here represents the boiling point of component A. This is the boiling point of component B. We see that the boiling point of component A is a lot lower than that of B, so component A is the more volatile liquid. And so at this first boiling point that we were looking at, the vapor phase has a much higher concentration in component A than the liquid phase. We say that the vapor is enriched in component A, the more volatile liquid. And so if you cooled that solution down, that vapor down, you condensed it down, and then reboiled it, okay, so you went back down to the liquid phase where component A is larger now. Then you boil that solution. Once that solution starts boiling, you then look at the vapor above that boiling solution, and it'll be even more enriched in component A. So you see that that the next boiling, or the next vapor phase, is even more enriched in that more volatile component. And you can repeat that. You cool it down, bring it back up to a vapor. The next vapor that you collect and condense is going to be even more enriched. And you can just continue doing that until you in this case, until you essentially purify that condensate to be pure component A. So that's something that we call fractional distillation, and I think I have a couple of pictures later on discussing that again. What do they want us to do here? It's really just generating a graph. And so it's generating a temperature composition graph. And so what they're plotting, what they're giving you is they're giving you temperatures and concentrations. Okay, so notice that the temperature 110.19 degrees Celsius has two values associated with it. At 112 degrees Celsius, there's two values associated with it. So this is where you have to think sideways. Okay, so it's like 110. Well, let's do something in the middle. Let's do 115. Okay, it has a value of 0.5 and 0.6. So at 115, you draw a horizontal line and then you plot those 2 points. So notice how they're both at the same temperature. They're on the same horizontal line. Each of the data points is like that. So these guys are paired. Those guys are paired at the same temperature. These two are paired. So are those and those, etc. And then the ones at the ends, those are the pure component boiling points. Okay, so that's how these temperature composition diagrams are constructed. So you have to think sideways, that I've got a particular temperature and I know the composition of the two components. I know the liquid composition and I know the vapor composition. So you plot them, you plot the points as pairs, and then the graph here, or the curve then, in this case, is they wanted you to do a third-degree polynomial fit to that data. So for each of the curves here, you've got a set of y data. I shouldn't say y, I should say, you've got the dependent variable here as a function of the independent variable, and you've got another data set here for the vapor phase. What they're asking you to do for each of the data sets is to fit the temperature as a function of, as a third-degree polynomial. I'm going to use the variable z to denote either x or y. So this is going to be your concentration variable. They want you to do a fit like this. So fit the boiling point as a third-degree polynomial. I'm going to go ahead and skip how to do that. You can do it pretty easily in Mathematica. You can probably do it in Excel, although I'm not very sure. I know you can do it in Mathematica. If you're interested in that, let me know. On the next, what's next is we're going to describe something called the lever rule in temperature composition diagrams. It's a lot of equations, and I don't feel like you get that much value out of it, but I'm going to present it just in case some of you go into physical chemistry involving solutions. So first we're going to take a look at the phase diagram again, another figure, and I'm going to distinguish between what are called the isopleths and the tie lines. So here's another diagram. Notice it's reversed. The orientation is reversed. In this case, so we're plotting it as a function, temperature as a function of component A. So when you're at pure component A, we see that the boiling point of pure component A is larger than that of component B. So in this case, in this diagram, component B is more volatile than component A. But you can plot it as component A or component B, whichever one you choose. Whichever one's more volatile is going to determine whether the graph goes up or down. In any case, so it's the same type of diagram. Temperature as a function of concentration. The isopleth is this vertical line. Okay, and so here this axis, this ZA, this is overall concentration. So the overall concentration of the solution, Z. So when you're in the liquid phase, whatever this value of A is, that's your overall concentration. And then when you look at the two curves here, for the bottom curve, you can think of the Z as being X. And when you look at the upper curve, you can think of the Z axis here as being Y. That is the mole fraction of component A in the liquid phase versus the mole fraction of component A in the vapor phase. So this vertical line is called the isopleth, and then these lines that move across, these are called the tie lines. Okay, so various tie lines. Now, what I have here on the slide they're just simple definitions, but because there's multiple components and multiple phases, it gets a little hairy just because there's just so many different ways to express concentration. And so here is the formal definition of XA. So this would be the mole fraction of component A in the liquid phase. It's the number of moles of component A in the liquid phase divided by the total number of moles of liquid. The mole fraction of component A in the vapor phase is the number of moles of component A in the vapor phase divided by the total number of moles in the vapor phase. And then this is the overall concentration, Z. Total number of moles of A divided by total number of moles. And the number of moles of component A, part of it is in the liquid phase, plus another part is in the vapor phase. And the total number of moles. There's a certain number of moles in the liquid phase and a certain number of moles in the volume phase. Okay, so using all of these definitions, you eventually wind up with what's called the lever rule, which is right here. And so this L, this little l subscript L, and this little l subscript V, these refer to distances from the, along the tie line from the curve to the isopleth that you're interested in. So if you're interested in a particular isopleth here, you have these two distances, LV and LL, in this notation. And, okay, the distances here are related to the number of moles in the liquid phase versus the number of moles in the vapor phase. So here, this is explicitly what those distances are, right? The value of ZA. So you have here XA minus the value of ZA. That's that distance here. This distance here is ZA minus YA. And so that's the whole point of this, is that you can use the diagram to determine what's the relative amount of liquid to volume. So, for example, you can take the lever rule and rearrange it either way you want. You just make this ratio here. So if you've got the diagram handy and you're interested in a particular isotope, a particular isopleth, you can bust out your ruler, measure the distances, and then it's going to tell you the relative amounts of liquid and water, or of liquid and vapor phase. And so that's what this illustration is talking about here. Okay, it's using the previous diagram to discuss the relative distances between the isopleth and the curves for the different at the different tie lines, and then you can then make a comment about how many molecules there are in the liquid phase versus how many molecules there are in the vapor phase, and so that's what's going on here in these different curves. Let me move on to the next. This is the more interesting topic, in my opinion. So the idea of distillation, I've already talked about it a little bit. As we said before, when you've got a binary mixture of volatile liquids, the vapor phase is always more enriched in the vapor phase is more enriched in the more volatile liquid. And so for certain types of solutions, particularly those involving a non-volatile liquid or solid, you can separate or I should have said solute. You can separate the solute from the solvent using simple distillation. For example, if you had salt water, you could, in principle, if you needed to purify the water, you could do a simple distillation to boil the water, collect the vapor, condense it, and then you would have purified water. Or, if you had two volatile liquids, depending on the liquids, you can separate them through that fractional distillation method that I talked about before. And this exercise here corresponds to this diagram where that is discussed. And so here we've got two cases. In the first case, we've got two volatile liquids whose boiling points are pretty far apart from one another. And so let's suppose that we started with a solution that had this concentration in the liquid phase, and we can boil it. We get the solution boiling. We collect the vapor. We condense it. We boil it, collect the vapor, condense it, boil it, collect the vapor, and it takes roughly 3 attempts to get to this level of purity in component A. So we call these theoretical plates. So there are 3 theoretical plates to get from this concentration to that concentration of a solution. You can see when the boiling points are closer together, in order to get to this, in order to achieve the same amount of purity, you have to engage in more theoretical plates. You have to go through 4 theoretical plates to get the solution to the same level of purity. So when the boiling points are closer together, you have to go through more cycles of boiling and condensing. It's even more interesting when the interactions between the 2 components of the liquid are such that the solution is not very ideal at all. So when you have a solution that's really, really deviating a lot from ideal behavior, you get some interesting effects in these phase diagrams. You can form what's called an azeotrope. An azeotrope is a solution where the liquid phase and the vapor phase in equilibrium, when they have the same concentration. And in these cases, when a mixture forms an azeotrope, you can't separate the components by simple and fractional distillation methods. You have to resort to more complex methods that I won't go into. I'm simply going to describe the temperature composition diagram for the azeotropes. And you can classify these as 2 types, although they go by different names, although they have different names for them. One of them is called a maximum boiling azeotrope. Also, it's called a negative azeotrope. Or you can have a minimum boiling azeotrope, which is also called a positive azeotrope. For the maximum boiling azeotrope, there are favorable interactions between the 2 components that end up stabilizing the solution, making it more difficult to boil. For the minimum boiling azeotrope, the interactions between A and B are less favorable, which in a sense destabilizes the solution and makes it, relatively speaking, more easy to boil. So here's an example of a positive, a high boiling azeotrope, which is called, I always get this confused, it's called negative. And so I typically prefer the maximum boiling azeotrope because it's easier to visually see, but that's just me. In any case, so here we've got, so this is the temperature composition diagram. It's the same diagram we were looking at before. So these are the isopleths, different isopleths. And you would interpret this axis as being the overall composition. When you're looking at the blue curve, you're talking about the mole fraction of component A. In the liquid phase, when you're looking at the red curve, you're talking about the mole fraction of component A in the vapor phase. And so what happens when you have this crazy deviation from ideal behavior? What it means is that you can, for example, let's suppose you take an overall solution, a solution with this overall composition, and then you start to boil it and pull off the liquid phase. Well, what happens to what's left behind is it starts to become more and more concentrated in the liquid phase. As you continue to boil it, will become more and more concentrated in the non-volatile component. And so what's going to happen as you continue to boil that mixture, the solution is going to, the liquid phase is going to start drifting towards this point B here. But at this point, the liquid phase and the vapor phase have the same composition. And so by continuing to boil, you you do not enrich the vapor phase or deplete the liquid phase any further. And so essentially you get stuck at this point, which this particular concentration is called the azeotrope. Here's an example of that low boiling or minimum boiling azeotrope, the so-called positive azeotrope. The situation is similar in the sense that, let's suppose that you start with a solution with this concentration, this overall concentration, and you get it boiling. You condense the vapor, or you collect the vapor, which has this concentration. You condense it, reboil it, collect, condense, etc. You eventually get stuck at this point B, and this is the azeotrope here. So in the case of the positive, I keep doing that. In the case of the maximum boiling azeotrope, the interactions between the two components A and B are more favorable, and so that's why it takes higher temperatures to boil the solution than you would expect compared to the ideal solution, right? The ideal solution would be like two curves, one going this way, another one going that way, but both going down. Here we've got this sort of positive deviation from that, even though this is called the negative azeotrope. Again, the lingo is hard to keep straight when you first learn it and when you get tongue-tied. In any case, this indicates, this peak here, the maximum, indicates that the interactions between the two components are more favorable than they are for the pure components. Here, this minimum boiling azeotrope, it indicates that it's a bit easier to boil the azeotrope or the solution compared to the pure components, and so you would say that the interactions between the two components are a bit weaker than they are between the pure components themselves. This slide, there's nothing to this exercise. It just highlights a few examples of azeotropes. So it says that these first three mixtures, I believe, are like the maximum boiling azeotropes, and then examples like that would be minimum boiling azeotropes are these two here. So ethanol and water, that would be an example of a minimum boiling azeotrope. And so with that, I think I'm going to go ahead and stop this video, and we'll pick up again with the next section. We're going to skip over a couple of topics, and we're going to work on activities.